Suppose we have a system that looks like this. We say our solution to a system of this form looks like x is equal to e to the power lambda t times v, where lambda is our eigenvalue, and v is our eigenvector. We find out both of these, the eigenvector and eigenvalue, from working with this formula. Now, when you find the eigenvalues, either from finding the determinant of a minus lambda I and equating it to 0, or lambda squared minus the trace of a lambda plus the determinant of a is equal to 0, and they turn out to be complex, they will always come in complex conjugates, which means if you solve this very equation or using this, you will get two eigenvalues which will be complex conjugates. Now let's see how we deal with these through some examples. So suppose we have a system 1, 3, negative 3, 1. As before, we assume that the solution is of form this, and we use this formula to get our eigenvalues and vectors. Now I'm going to use our shortcut, basically this equation, which is also actually known as a characteristic equation. So lambda squared minus the trace of a lambda plus delta a is equal to 0. Over here, this is a. So the trace of a is 1 plus 1, 2. And the determinant of a is 1 plus 9, which is 10. So our equation becomes lambda squared minus 2 lambda plus 10 is equal to 0. Now if you put this in a calculator, it'll give you an error. So we will see how we can use the quadratic formula. So that is 2 plus or minus 4 minus 4 times 1 times 10 divided by 2. Now this turns out to be 2 plus or minus square root of negative 36, which is 2 plus or minus 6i over 2. And that is 1 plus or minus 3i. So there you have it, folks, your eigenvalues. So to find eigenvectors, we have to deal with each of these individually. So for our first one, let's take 1 plus 3i. So what we're going to do is we're going to perform this operation. So a minus lambda I. So that is 1 minus lambda 3, negative 3, 1 minus lambda. times v equal to 0. And if you put in this lambda over here and here, you get negative 3i, 3, negative 3, negative 3i. Okay, so performing row operations on the first row, I get negative 3i v1 plus 3v2 is equal to 0, which is the same as I v1 is equal to v2. Now I'm going to let v1 is equal to 1. You can choose anything, just don't choose a 0, because then we'll have a trivial solution. Now if we let v1 be 1, I always choose 1 when I can because it just makes everything easier. Then v2 is I times v1, which is I. So this will give us our first eigenvector. v1, v2, and those are 1, I. Now the same exact thing to the second eigenvalue, which is doing the same exact thing, plugging in this eigenvalue into here, you will get 3i, 3, negative 3, 3i times v1, v2 is equal to 0. Again, row operations, I'll just use the first row. You get 3i v1 plus 3v2 is equal to 0, which is the same as I v1 is equal to negative v2. Again, I'm going to let v1 be 1, then my v2 is equal to negative I. So we have a v1, we have a v2. We can write our second eigenvector as 1, negative I. Now, let's write our two solutions because now we have two eigenvectors and we have two eigenvalues. So our solution, which was of this form, first one is e to the power first eigenvalue, which is 1 plus 3i times t, times the first eigenvector, which is 1i. Same thing for the second one, e 1 minus 3i times t, 1 negative I. Now, it's not common to want complex solutions to our system, especially if it's differential equations. So what do we do with these i's? Because we don't like them. Now, Euler's formula is one way that we can use to transform our solution. It's not very straightforward, but we'll get there eventually. So his formula says that e to the power it is equal to cosine t plus I sine t. Now what we will do is we will substitute this into the solutions we have found to get rid of I. Now take the first solution. Which is x1 is equal to e to the power 1 plus 3i times t 1i. Now this can also be written as e to the power t times e to the power 3it times 1I. That's just simple algebraic manipulation. Now if e to the power it equals to this, then if I substitute 3t whenever I see t, I will get e to the power 3it. So that is cosine 3t plus I sine 3t. So wherever there was a t, I substituted a 3t. So when I put this here, what happens? Then I get e to the power t times cosine 3t plus I sine t. I sine 3t times 1I. Multiply throughout. So you get one vector. You will get e to the power t cosine 3t plus e to the power t times I sine 3t. Second one, I e to the power t cosine 3t minus e to the power t sine 3t. Now, the next step is you're going to separate the real terms and the imaginary terms. So here, this is real and this is real. This is imaginary, this is imaginary. Basically, whichever term has an I is imaginary. So if we separate these, we get e to the power t cosine 3t negative e to the power t sine 3t plus I'm just taking the I out, e to the power t sine 3t and e to the power t cosine 3t. Okay, now let's call the real part. All of this u of t, you can call it with whatever variable you want. And let's call this v of t. Then, if I substitute u and v in for this and this, I get x1 is equal to u of t plus I v of t. U and v both satisfy a system of this form and are solutions of it, and this can be proved. So, if these two can be solutions, then the principle of superposition says that their sum, 2, is a solution. So, our general solution to this becomes b1, which is a constant, u of t plus b2, which is again a constant, v of t. So this is the general solution if you have complex eigenvalues. Now notice we only used x1 to get the solution. This has to do with the fact that the eigenvalues lambda 1 and lambda 2 are complex conjugates. So if you do a similar operation on x2, the second solution, this solution right here, you will get the same u and v, and that's all we need for our solution over here. So using x1 or x2, the first or the second solutions, is not of much importance. Any is okay. So our final solution to the problem we were actually working with right here becomes x is equal to b1. I'm going to take e to the power t out of everything. Cosine 3t sine 3t plus b2 e to the power t sine 3t cosine 3t. I'm sorry, this has a negative sign. And there you go. We're done. This is the final solution. Let's see another example. We'll do this one a bit quicker. Let's say we have this system. Again, our assumed form of the solution is this. And how we find our eigenvalues and eigenvectors is this. So I'm going to use the shortcut to find the eigenvalues, which is this. And here, this is A, the A that we're talking about here. So the trace of A is equal to -4, and the determinant of A is equal to 5. So this equation becomes lambda squared plus 4 lambda plus 5 is equal to 0. Now if you solve this using the quadratic formula that I showed, you will get lambda is equal to -2 plus or minus I. Okay, now as usual, we will deal with each of these separately. -2 plus I. Then if you do this business now, which is A minus lambda I, we get -2 minus lambda, -1, 1, -2 minus lambda. Now if you substitute this here and here, you should get -I, -1, 1, -I. Row operations, I'll use the first row. You get -I v1 minus v2 is equal to 0. So -I v1 is equal to v2. I'm going to let v1 is equal to 1. Then v2 is equal to negative I. So our first eigenvector becomes 1, negative I. Now we don't really need to calculate the second eigenvector, since the eigenvalues occur in conjugates. The second eigenvector is also a conjugate of the first eigenvector. So the second eigenvector, if you do the math, should turn out to be 1i. So the first solution becomes e to the power negative 2 plus I times t times 1 minus I. And the second one is e to the power negative 2 minus I times t, 1 I. Okay, so again, let's use the first solution to get our u and v, which will help us write the final solution. So we can write this as e to the power negative 2t times e to the power it, 1 negative I. Now we said e to the power it is cosine t plus I sine t by Euler's formula. So substituting this here gives me e to the power negative 2t times cosine t plus I sine t, 1 negative I. Now if you just multiply throughout, you should get e to the negative 2t cosine t plus e to the negative 2t I sine t. Second row, negative I e to the negative 2t cosine t plus e to the negative 2t sine t. You will separate the imaginary and the real parts. So real, real, imaginary, imaginary. So by separating, we get e to the negative 2t cosine t and e to the negative 2t sine t plus I e to the negative 2t sine t and negative e to the 2t cosine t. I know this is a lot of sines and cosines. So this, the real part, is what we said that we're going to call u. And this part, we said we are going to call v. Go ahead and choose what you want. I mean, the variable. You can use a or b. So our x, the solution, which is of the form b1 ut plus b2 vt, should be of the form b1 e to the negative 2t. Now I'm taking e to the power negative 2t out of everything out. It's everywhere. Cosine t sine t plus b2 e to the negative 2t times sine t negative cosine t. You can very much go ahead and keep these inside and just, you can write the final solution by just adding constants over here and eliminating the I. That's okay too. But I just choose to put these e to the power 2t to the power negative 2t out because it just makes things look better.